Hi everyone, and welcome to today's webinar, which is Unlock the Secrets of Masonry Art Analysis with LimitState Ring. I'm Tom Pritchard, Principal Engineer here at LimitState, and I'll be your host. And over the next half an hour, we'll take a closer look at some of the features and capabilities of LimitState Ring, our powerful software for analyzing masonry arch bridges. There'll be some time for questions towards the end, so please do feel free to post these in the webinar interface as we go along. I know we've got a mix of attendees today. Some of you are quite new to the software, while others will be seasoned professionals. I do hope that everybody leaves with some fresh insights into what you can achieve with LimitState Ring. So preparing this session, it became quite clear to me that there are far too many tips and tricks to fit into just this one half an hour. So I'm planning also to do follow-up webinar or two to explore the areas that we don't actually touch on today. So with that in mind, let's take a look at what's coming up in today's session. So we'll kick things off with a quick introduction and then dive very quickly into the effective bridge width and lanes and how they work in Ring and what things you might want to be watching out for. After that, we'll take a look at multi-ring arches and near surface concrete slabs and how these features can be modeled and how they will affect real world behavior. And then we will finish by considering abutment reactions. And then we'll have a quick summary and a chance for you to ask any questions. So we go on. First thing to note is that masonry arch bridges are some of the most durable and important parts of our transport infrastructure, both here in the UK and widely across Europe and the rest of the world. But like all aging assets, they do face increasing challenges, not just from time, but from the heavy demands of modern traffic as well. When it comes to assessing these structures, it's often dealing with these minor details, as we would see them, whether part of the original construction or as later retrofitting and repairs that cause the most difficulty when modeling them, both within LimitState Ring and using other methods. And many of the topics that we'll look at today come directly from real world questions and support queries from our users. So hopefully you'll find plenty that resonates with your own experiences. Just in case you're completely new to the software, very quickly we'll cover what is LimitState Ring. At its core, it's an industry-leading tool for performing ultimate limit state analysis, that is, plastic analysis of masonry arch bridges. It has its roots in the work of Professor Matthew Gilbert during the 1990s and 2000s, and it uses the rigid block method as pioneered by Heyman earlier in the 20th century. The main outputs of the software are the load capacity, or adequacy factor as we call it, of the arch and the associated failure. That mechanism can involve hinging, crushing, sliding, or some combination of all three of those. Beyond the standard ULS analysis, Ring can also account for support movements, which we'll come back to later, and the more recent versions of it also allow for what's called a permissible limit state analysis, following the approach to service loading described in Syria Guide C800. So let's take a look at the effective bridge width. So selecting an appropriate effective bridge width is actually a really important thing because it acts as a direct multiplier of the numeric solution or the adequacy factor. It's not just, some people tend to do when they first come to the software, just putting in the total bridge width. It's actually a measure of the transverse width of the arch barrel that is resisting the applied load. So it's very important that we provide a proper and realistic value for this effective bridge width. And because Ring is a 2D analysis tool, we're essentially within the software assuming a 1 meter strip under plane strain conditions and then multiplying up the results for that by the effective bridge width to get our adequacy factor and our solution. So in simple terms, the effective width is made up of a few things. So either the axle or sleeper width at the surface level, the amount of load spread through the fill, and in Ring that distribution could be different for both the surface and the backfill materials, and then any extra distance that we want to include to account for distribution within the arch barrel. So that's mainly in highway codes. Railway codes tend to omit that part of it as well. And there are several factors that can influence the value of effective width, which include things like the proximity of a vehicle to the parapets, any longitudinal cracks or joints to the barrel, especially over the crown, the presence of adjacent lanes, which we'll look at in a second as well, and indirectly centrifugal forces as well. So getting the value of effective width right is key to producing a realistic analysis in ring. So the Ring User Manual provides a lot of guidance on selecting an appropriate effective bridge width, and this is based largely on the historic UK codes of practice for both highway and railway bridges. So it's quite important to remember that the effective width depends on the depth of the load position under consideration. And you'll also, like we say, need to account for significant cracks or joints in the arch barrel. So where mechanical bonding is absent, the load might not distribute effectively across to the separate parts of the barrel. And that's particularly critical over the crown where the fill depth is lower and there's less material to help, backfill material to help spread the forces before they reach the brickwork. So in many cases, the most demanding situation for a crack structure will occur when there's a wheel positioned directly over the location of a crack and there's very little opportunity for that load to spread out before it reaches the barrel. You should also consider all possible loading scenarios. So on wider bridges, for example, a vehicle with one wheel on the pavement, for instance, if it's parking or going around something else, can quite often place loads close to the parapet or over joints that aren't directly beneath the main carriageway. So we need to consider as many of these loading situations as we possibly can that we believe would be realistic. And then by carefully considering these factors, you can ensure that the effective bridge width reflects the most critical conditions to provide a safe and realistic analysis. If you're in the software specifying, and we'll look at this in a second, a fixed effective width, it should correspond to the location where the value is at its minimum across the structure. So this avoids us overestimating the arch's resistance. Alternatively, Ring can also auto-calculate, we can see here, the spread of load whilst also allowing you to set maximum effective bridge width limits. So the software will automatically curtail the spread if it exceeds that value. So probably the easiest thing to do is if I grab the software, we can take a quick look at it here. And I'm just going to set up, for the sake of argument, a default bridge. So click Finish on the wizard. I'm sure a lot of you are familiar with this already. Just a single span and a 100 kilonewton load. If we open the project details dialog, we can see here we're currently looking at a highway with a specified effective bridge width of 2.5 meters. You can switch to the auto computed, click on more and see how those spreads can be changed. In this case, the maximum effective bridge width is 5 meters, and we have, that's useful field to be able to put in a maximum value for crack structures, for instance. So if we know, for instance, that the distance between two cracks over the ground is 3.8 meters, then we might want to curtail our spread of load to that 3.8 meters. In this case, we'll leave it at 5 meters. You can also specify the spread to the near and far sides of the bridge. So the near side is the one that you're looking at in elevation in the software, and the far side is this theoretical one into the page. And being able to change the value of spread is handy for being able to model a vehicle being near to a parapet, or, as we touched on earlier, directly over the crack, because you can limit the spread in that particular direction. And something we'll touch on again later in the webinar is that the spread angle, so these ones here, the ones that are 26.6, may also be useful if you're considering near surface load relieving slabs, which we, like I say, cover in a second. So it's important, like I say, to remember that Ring is a 2D analysis tool. It's assuming this 1 meter transverse strip and then it's scaling the results according to the effective width. But for anything beyond narrow rural bridges that we often encounter multi-lane structures, So when you've got more than 2.5 meters, for instance, lane width, you go into 2 or 3 lanes. And how does this fit with the 2D? Common question we get asked is, how do we model multiple lanes in Ring? Because the software doesn't directly account for it. And where the loads overlap at the arch barrel, we recommend following the approaches that are outlined in references such as CS454 or Network Rails CEO25, similar guidance to that. If the lanes don't overlap, then you can simply analyze each one of them separately. And this approach ensures that your analysis will remain realistic and robust while still working within the 2D framework of the software. So here we can see the effective width to use in the analysis of a multi-lane problem should generally be equal to the total load spread over all the lanes if there's overlap, divided by the number of lanes that you have. On screen now we can see the effective width figures on the left-hand side from CS454 and BB21 from before that, and on the right is Network Rail CEC 025. They're very similar aspects of how to determine this effective width. It can be a little tricky to interpret them, especially the CS454 figure, but effectively the auto computer values in Ring correspond to these references. So when you switch from highway to railway settings, the load spread through the backfill and the additional width of arch to include, so 0 in the railway case, and other parameters are updated accordingly. Coming back to the multiple lanes, like say, remember that Ring is mapping everything back to a single lane. Essentially, that means that we're assuming the same vehicle or vehicles are present in each of those lanes transversely, which in the majority of the cases would be a worst case scenario. Additionally, certainly you can see it here in the Network Rail one, codes are generally happy to discount superposition of load where it overlaps towards the barrel, and our approach in Ring follows that same principle. So that was a little about effective width and multiple lanes. We're going to touch now on multiple ring arches. So another potential stumbling block in a ring analysis arises when dealing with multiple ring barrels. So we can see here we've got, actually this is out of the example files that get shipped with the software. It's a very large bridge, big span, high rise with lots of rings and also lots of blocks in each ring. And it can be tempting to model every ring and every block in the structure. After all, it's physically there and modeling everything seems like it should give the most accurate solution for you. However, including every single block can often be computationally expensive, often with little gain in accuracy. And this is especially true when you're starting to look at larger multi-span structures like viaducts. So to help with this, Ring will include a soft limit on the problem size, which prevents solving models that are generally excessively large or time consuming. So again, let's have a quick look at that. So if I cancel out of this, what we can see here is if I go to Tools, Preferences, Solve, we have a problem size group here where at the moment my maximum problem size is 10 times 10 to the 6, but the current problem, which is a very simple one, is only 0.35 times 10 to the 6. So effectively, what this is it's a count for the matrix size. And what we want to do is, if we ever get a diagnostic warning that says this problem is too large and you've hit the limit, you can come in, you can change this value, and it allows a sense check on something, so you don't click go and then find that it's going to take several hours to solve or something like that. Generally speaking, the software is very quick and most things will solve in a few minutes. But if you do get to the point where you're looking at, say, 10 or 11 span, Ring has 120 blocks in it, that can be quite a time-consuming problem to solve, as we will see if we go through to the next slide. Effectively, the problem size in Ring is related to the number of blocks, the number of axles, and the number of load cases. So that determines the matrix size. So if we can keep that as low as possible while still being accurate, that will allow us to solve them very quickly and efficiently. By default, ring uses 40 blocks per ring, which we've found provides a good balance between computational efficiency and solution accuracy. And so you can see in the figure here, we've got adequacy factor versus a number of blocks, and you'll notice that it goes down, wiggles about a bit, converges at around the 70 block point. But importantly, the largest drop occurs much earlier, and the error at 40 blocks is only about 0.4%, which is very acceptable. Now, you might argue that most real-world bridges aren't as simple as this, and even more complex structures do give results within a few percent of this true converged solution when we're using 40 blocks per ring. So this approach keeps ring fast, efficient, and this is especially helpful when analyzing larger or more complex structure. One of the other things that we run into with multi-ring spans is, of course, ring separation. So that's a quasi-brittle phenomenon where structures that lack mechanical bonding along the circumferential layers are particularly susceptible to this. So on the right-hand side here, we've got some stuff out of Series C800. We can see where we have separate arch rings, then delamination has a lot of opportunity to occur. Where we have some intermediate header bonded rings, then we have fewer opportunities, but they're still there. The best one of all is when we have headers between all of the rings, because that means generally that we have to shear the masonry itself rather than the mortar lines in order to create failure. It's difficult, though, to determine whether a structure often has observed delamination or ring separation. You can use hammer tests, cores, visual inspection, and things like that. But because it's a quasi-brittle phenomenon, the onset is often difficult to capture, and it can be quite quick. So because of that, because of the upshot of having full delamination along the rings, ring assumes full delamination by default, and that gives a low adequacy factor in a lot of cases, which can lead to some confusion. It's important to remember that some clients may be comfortable considering a single or reduced number of rings in certain circumstances if you have multiple rings. Even for an unbonded barrel, they might have decades of site inspection data that don't show any evidence of ring separation, and they might be willing to assume that's the case moving forwards. So it's always worth discussing that. But sometimes we want to consider an intermediate situation somewhere between full delamination and full fixity. We might have evidence of ring separation over the crown of a bridge, for instance, but none towards the abutments. And in ring, there are two approaches that we can use for modeling this. We can either glue blocks together, or we can add a shear bond strength or adhesion to the contact surfaces. Both methods involve the contacts in some way, allowing the software to capture this partial bonding effects realistically. So I'll jump back into the software again, and we can have a quick look at it. So what I'm going to do is I'm going to open a file that's about made. This we can see here, this is a very simple problem with two rings. If I solve it, I've just left the loading at the critical low position to avoid having to do an auto locate. So we can see here that the adequacy factor is actually, it's quite close to 1, but it's still underneath 1 at 0.92. And this is assuming full delamination around Abutment. What we might want to do is say, okay, we have only delamination over the crown. Towards the abutments and the springing points, everything's fine. If we want to glue things together, what we tend to do is select the lasso, draw a line around contacts that we want to glue together. It's worth noting here before I let go, if the lasso is red, then that's everything within the lasso is selected. If it's green, then it's everything that the lasso is touching. So here, if I do that, we can see I've selected all of those contacts, and I can do the same around the other edge. Here I've got control held down so that I can select lots of things at once. And then we come into the property editor. We can see the failure types for the contacts is expanded. And what we're going to do is just turn off the ability for those contacts to fail by hinging or by sliding. We want to keep on the crushing so that we can allow the masonry to fail in that way if possible, or if it wants to. So we have true, false, false set. And then if I resolve the problem, we'll have a warning just to say that we've got disabled hinging and on some of the contacts, but we know that. If I click OK, now we can see that our adequacy factor has gone up from 0.9194 to 1.11 by gluing these blocks together. And with this, we have a good method of allowing us to model mechanical bonding between layers realistically. Back here, so yeah, so this is just outlining the method that we've used, and obviously saying that we should use the diagnostics as well. I won't go into too much detail into it, but if you have different numbers of blocks per ring, or if the profile is not a nice smooth segment of an arch, then you can get staggering between the radial contact surfaces, and in that situation we have to be careful not to glue every single circumferential contact, because what we end up doing then is effectively gluing all the blocks together and creating a monolith, which can then give us a solution that has an adequacy factor and a failure mode that are not credible. They're too high in terms of resistance, and the failure mode will try and sort of fail the entire arch as a monolith rather than the individual blocks. The other thing we can do is, like we said, look at the shear bond, which is another way to restore some strength along the contacts. As with most features in Ring, it can be applied object by object, but for this demonstration, we'll look at it globally as well. On the left here, we can see the default frictional response along the contacts, which is the standard in Ring 4 and was the only option available to you in previous versions of Ring. Here, the shear stress along the contact is calculated as the normal stress just multiplied by the friction coefficient, giving it a standard frictional response. It's important to note that there's zero shear resistance when the normal force is zero. In Ring 4, we've got this concept of a pedestal C here, or an intercept on the shear stress axis, which allows the contact to resist a small amount of shear stress even before the frictional response kicks in. And this represents the shear bond strength or adhesion, and it can be adjusted to model partial bonding between rings in a slightly more realistic manner. It allows you to explore what-if scenarios and better understand the capacity of structures, particularly, like we say, for bridges with multi-ring spans. But there is a key caveat in that the ring is assuming the shear bond failure is ductile, which doesn't fully represent this quasi-brittle behavior that we often observe in practice with delamination. So to account for this, we recommend that you use a suitably low effective value for the shear bond strength. And in the user manual, we reference Hendry, who suggests a value in the range of about 0.15 to 0.35 newtons per millimeter squared. This approach allows the analysis to remain realistic but somewhat conservative, while still benefiting from the flexibility of modeling this partial bonding strength. So if I go back to software, and let's go back to this before we glued the blocks, so we can see here we know the solution without any measures taken is 0.9194. If I come into the material properties and just on the inter-ring contacts set a shear bond strength at 0.15, click OK and solve again, you'll see we get a warning to tell us about this positive shear bond strength, because it's something that we need people to be careful with. But if we're okay with it, we can solve again, and we can see that our adequacy factor here has gone up by a factor of about 55%. And we can see that along this circumferential contact here, we have, in this particular case, no delamination occurring. So while this functionality was a direct result of customer requests, we do still recommend that it's used with extreme caution, hence not considering it by default, and the warnings provided if there is a positive value there. So the next thing I'm going to have a quick look at is near surface slabs. So they're a reasonably common method of increasing resistance via increasing the load distribution within a masonry arch bridge. We can't model them directly in Ring, but we're able to simulate the effects of them. So as long as the slab extends along past the abutments, then we can look at them. We can increase the longitudinal load spread and also the transverse load spread if we deem it appropriate. It's been validated against sulfur bridge test results, which were some tests conducted in the late 90s and early 2000s. I won't go into too much detail about it, but effectively what we're looking at is dividing the load from an axle into a 1-to-1 ratio, so a bit like you would do with railway loading going through sleepers. And then if that axle is subject to dynamic loading as well, then you would apply the dynamic factor to all three of those axles. So again, let's look at software. If I this file, we can see here, I have the bridge that we just saw on screen. I've got, in this particular case, a single load and also another scenario where I've made that load into a slab. We look in the vehicle database here. That's the single load. And then the slab version, we have taken the span, divided it by 6, added extra axles at those locations, and then divided up the loading into 3. So 25%, 50% over the middle, and then 25% again. By then solve both these problems. In this case, we've got an auto load case running over it. We can see what the difference between a single axle assumption and this slab distribution assumption is. See here, solving. Once it's done in a few seconds, what I'll do is I'll expand this upwards and we can have a look at the graph very quickly. So we have our solution. We can see, as we would expect, that the critical adequacy factor is to do with the single axle. If we switch to the 3-axle representation, let's see where that looks critical. So the blue line here is our single axle, and our critical scenario is that. The critical scenario for the slab version is in a very similar position, but what we can see here is if I hover over that again, that adequacy factor has actually gone up to 1.25 approximately compared to 0.87. So that increase in longitudinal load spread in this particular case has been enough to allow us to class that structure as being safe for the conditions that we provided it with. If we found that it was still below that adequacy factor of 1, what we can also do is then start looking at the transverse load spread as well, because a concrete slab may allow us to increase our load spread from the 26.6 degrees if we're looking at highway load to something maybe more like 45 degrees, and that would allow us an extra bit of effective width, which would then increase the adequacy factor that we were looking at. But again, this is something that you would need to be able to justify from an engineering point of view. Similarly, if you've got a slab that lies over cracks or joints within the structure, then you could potentially consider that then negates the effects of the crack from stopping that load spread from getting to all parts of the arch. So again, you might be able to increase the effective width that way. Looked at these. The last thing I'm going to look at very quickly, I'm conscious that time is almost run out, is abutment reactions. So both at collapse and under service loading, understanding the forces of the supports can be very useful. For instance, if you're doing work at the foundation level, you'll need to think about a collapse. You can just query the forces after performing a normal and ultimate limit state solve within Ring. But we need to keep in mind that the forces aren't necessarily unique at non-yielding locations. That's a fundamental part of the plastic analysis that we're undertaking, is that the uniqueness is only guaranteed at the points of collapse, so where hinges sliding or crushing are occurring. Away from those, you could have various equilibrium states that could be valid. The values are generally in the right ballpark, but like I say, they're not necessarily unique. In service, you can use Ring's support movement functionality to assess these service conditions. So I'll jump back into the software again. And what we'll do is we'll do a very quick 2-span with 3 meter here. So here's our problem. If we're looking at the support movement, what we need to do is move our load to a position where we feel it might be critical. So over the quarter span of this first span is fine. Let's just set that to a single. In support movement mode, we're introducing releases into the structure itself rather than increasing the live loading to drive collapse. So as if maybe centering has been taken out and it's settled a little, you might get these relaxations. But what we want to do, if we go to Tools, Support Movement Wizard, I'm going to pick, in this particular case, the bottom of the pier, and I'm just going to move that support by a distance of 1 downwards. And then when I solve, what you'll see is you can select that contact, and in the output part here, we can see what our shear, normal, or horizontal and vertical forces are. So in this particular case, we're looking at a normal force of 270 kilonewtons meter width. I can then go back, and instead of moving it down 1, I'll move it up 1. Again, query that contact force, and we can see here the normal force is 310. We can do the same to the left and the right, and from doing that, we can build up an envelope of likely support forces for different amounts of movement, and these are the forces for this particular loading situation. So if we go back to here, what we can see is just an explanation of what we've just done. If we repeat with different movements, upwards, downwards, left and right, we can then build up an envelope of the vertical and horizontal forces at that contact for the pointers failure in that particular situation. Sorry, service loading in that particular situation. So we've actually gone over by a few minutes, so I'll summarize very quickly and then I'll take 1 or 2 questions and then we shall wrap up. So we've explored a range of real-world scenarios in LimitState Ring. Many unusual situations can be modeled indirectly in one way or another. So if you do find that you are experiencing some sort of unusual geometry or features at your site, then do let us know and we can see if we can work out a way that we can model those either directly or indirectly within the software. But like I say, I realize that there are a lot of different things that might be useful to people, so we're going to have follow-up webinars to cover more tips and questions. If you do want to learn more outside of here, then there are various places. So obviously from our website, we also have a YouTube channel where all of these webinars are positioned. And also, if you ever have any questions, then do feel free to contact us either on info@limitstate.com, or you can contact our support team directly on support@limitstate.com. So final thing is, I'm just going to see if there are any questions. Actually, they've got a few. Yeah. Okay. One of them's asking modeling for multi-lanes. Can I go over it again? What I'll do is I will reply to you again afterwards. But this will be recorded and put up on the website, on the YouTube channel, so you should be able to see how to do that there. Another question is the software capable of modeling tie bars in the analysis, especially for jack arches? It's a difficult one for jack arches. Depending on the exact nature of the problem, there are some things that we can do in order to introduce forces at the block level to, for instance, show support, or if you're propping it, for instance, or something like that. But it depends what information you want out of it. Generally speaking, we tend to not assess jack arches if we can help it, but there are certain caveats. The final question, if I have a look, is can we model the effects of spandrel wall resistance? So again, we're looking at 2D analysis. So sort of secondary resistance that you might get from spandrel walls and things like that isn't taken into consideration by the software. Firstly, because we're looking at this sort of 2D plane straight strip, and obviously the wider the bridge gets, the less the effects of those spandrel wall restraints are going to be. But also, it's not a guaranteed resistance that you might get. So we don't consider that. If you're wanting to consider spandrel walls, then certainly something that's looking at more 3D FE approaches would be more useful at this present time. Okay, so I thank you everybody for joining. I'm conscious that I've gone slightly over, but if you do have any more questions, do feel free to get in contact. I will follow up on the questions that I didn't manage to answer during the webinar afterwards. And like I say, do keep an eye out for follow-up webinars that will touch on other topics to do with modeling things within LimitState. So thank you all again, and we'll speak to you all soon.